What's up, everybody? It's Dan from SageMathTutoring.com, and here we have a video covering what is called Euler's method. Now, Euler's method is a numerical method for approximating the solutions to ordinary differential equations, and it's named after Leonhard Euler, a Swiss mathematician who made important contributions to the field of mathematics in the 18th century. So let's get right to it. Basically, it's a way of, again, approximating the solutions to differential equations. So the process that I'm about to present you here is going to be pretty straightforward, and it does entail using a table like this, which is probably similar to sort of the typical calculus teacher, what the typical calculus teacher would sort of suggest. Now, there might be some differences here. For example, I'm kind of adding this column here. Sometimes there's only this column presented, but I'm going to add this column because I like to do everything like one small step at a time. So nonetheless, I think the best way to understand what's going on with Euler's method is to look at what's happening on a graph. And it is the case that Euler's method is a method that won't require a graph, but nonetheless, in order to understand it and to kind of understand what's going on behind the scenes, I'd like to present a graph. So let's imagine that this is the equation of a particular solution curve, y equals 1/4 x squared. And here we have sort of a first quadrant view of that solution curve. Now, let's say we didn't actually have access to either this graph or this the equation of the solution curve, but what we did have is we had this differential equation, which is, we could say, the derivative of the solution curve. And let's say we had not only this differential equation, but we also had what sometimes is called an initial condition, which is a point that we know for a fact happens to be on the solution curve. And in this case, that point would be 0, 0. So let's say it's only the yellow things that we have access to. We don't have this, and we actually don't have this either, but we only have these yellow boxes, as far as information. And the question is if we only have this differential equation and an initial condition, is that enough to actually approximate the solution curve, to approximate sort of various points that would be on the solution curve? And the answer is yes, and that's where Euler's method comes into play. All right. Now, not only am I going to kind of go through this problem in such a way that would be representative of what the typical AP calculus student would have to do in class, but I'm also going to provide a visual demonstration of what's happening as I go through the problem. And I think that's going to be helpful for any student watching to understand why we're doing what we're doing. Okay, so nonetheless, the way to go about it is to immediately get clear on what your so-called step size is going to be. Now, in this case, the step size is going to be 1. Now, the step size means change in x values, all right? Now, I'll just give you a little heads up about it. The smaller the step size, the more accurate the approximation is going to be. And the larger the step size, the less accurate the approximation is going to be. And you're going to see why in a moment. So let's imagine that the step size is 1. Well, what we would be doing is we would be constructing a table like this. I like to draw these parentheses because I know I'm going to be multiplying stuff. So I just draw empty parentheses here, okay? And you put the initial condition point in the beginning. So we have 0, 0. Again, that was a piece of information that was given right out the gate. All right, then what we do is, what I would suggest is have a whole column for just dy over dx. So what does dy over dx equal, given the fact that the initial point that we're analyzing is 0, 0? Well, dy over dx is apparently 1/2 x, okay? So obviously it's going to be 1/2 times 0, so that's going to be 0. So then I move to this column here, where it's going to be the step size times dy over dx. Well, actually, the step size is just 1, so I'm going to write that all the way down the line because we're going to be doing that every time. So it's going to be 1 times whatever dy over dx is. So that's clearly 0. Okay, so it's going to be 1 times 0, which is just 0. Now, here's the important thing. What this represents is the slope at this point. This represents the instantaneous slope at this point. So we're going to draw that first point here. Okay. Now, over and across a step size of 1, we're going to acknowledge an instantaneous slope of 0, which means that you're going to have an instantaneous slope of 0, which is a horizontal tangent line right here. Okay, but since it's a step size of 1, what we will be doing is we're going to be extending that tangent line, okay, all the way across a step size of 1. And that's going to give us a new point here. All right. Now that is a point that represents the first approximation. Now, could it be closer to the curve? Yes, but it's kind of close, right? It's not all the way down here. It's kind of close. All right. And as you're going to see, we're going to get kind of closer and closer as it goes on. But nonetheless, what are the coordinates of that point? Well, that's clearly 1, 0, right? That's clearly 1, 0. So we're going to write 1 and we're going to write 0 there, okay? Now, by the way, the step size, in a way, we could just sort of get this over with as well. We could say, we could flesh out the rest of the x column. It's 1, 2, 1, 2, 3, 4, because that's going to be the case, seeing as how the step size is 1. We're going to go 1, 1, 1, right? So now we could continue the process, okay? So based off of this sort of instantaneous slope at the initial starting condition, we're taking into account a step size of 1, and we just landed here, okay? So now we're going to do dy of dx as it pertains to this particular point. So what is the, the slope at that particular point? Well, it's going to be dy over dx, which is 1/2 times 1. And 1/2 times 1 is clearly 1/2, right? Now, the reason for this column here is, yes, this is the instantaneous slope, but the reason for this column is we're scaling this slope to this particular graph with the step size, okay? Now, you're going to see why in the next slide, why this column is so important. It's going to be a little less obvious why this column is so important because it's just 1 times dy over dx every single time. But in the next slide, the step size is going to be different. So you're going to see the importance of this column. Again, this column scales the instantaneous slope to the actual graph itself. So we have 1 times 1/2 here. Obviously, that's 1/2, right? So what that means is we're going to have a slope of 1/2 emanating from this point, all the way across the step size. So that's going to be a slope of 1/2. I'm going to go ahead and sort of try to draw that one. 1/2 would be up 1 over 2, right? 1, 2, but I want to scale that back to there, right? So that's the next point. So the next point is going to be right there. Now, as you can see already, our approximation graph is kind of tracking the curve. So this point is 2, 1/2, right? Now, the reason I'm drawing all these in greens is because it's in the color green is because this column, this green column, is the approximation column, where basically the typical Euler's method AP calculus problem is going to ask you for the so-called approximation at whenever x equals a particular value. In other words, they're going to be looking for one of these numbers in this column. Okay, so for example, if the AP calculus question was saying, what's using Euler's method, what's an approximation of this graph when x equals 2? Well, you would say the answer is 1/2. All right, so dy over dx, that's going to be 1/2 x again. So 1/2 of 2 is 1. So we're going to put a 1 there, and it's going to be 1 times 1, which is just 1. So that means we have a slope of 1 emanating out of this guy, right? And across that step size of 1. So we're going to go ahead and just draw that beautiful slope of 1, which would take us there, all right? So that would land us in that position. Now, clearly we could see that that's going to be 3 comma 1.5. Okay, so 3 comma 1.5. Now 1.5 is really 3 over 2. Okay, so far so good. And when it comes to this next column, dy over dx, it's going to be 1/2 of 3. Well, clearly that's going to be 3 over 2. So we're going to be multiplying 1 times 3 over 2 right here. And that, of course, is 3 over 2. So what that means is we're now going to have a slope emanating out of this point across the step size of 3 over 2. Now that is up 3 over 2. So I'll do my best to not confuse myself here. I mean, really, we could just use any interval up 3 over 2. So it's actually not that bad. So we could just go up 3 here and up 2 over, and that actually lands us where we need to be anyway. So that's going to be right here, and that is 4 comma 3. All right, and just for the heck of it, we'll fill out the rest. This could, of course, go on forever, but nonetheless, when we fill out dy over dx, that's going to be 1/2 of 4 in this case, so of course that's going to be 2. So that means we have an instantaneous slope of 2 associated with that point, and then 1 times 2 to scale that instantaneous slope is just going to be 2 itself. Now, that is going to be up 2 over 1, so that would land us, let's see, I'll just kind of say it would look something like up 2 over 1, something like that, right? So I'll just kind of make it a nice looking graph, so it'd be something along these lines. So nonetheless, that point would be like there-ish, right? So nonetheless, you can kind of see how these green points that I drew are decent approximations of the original solution curve. I'd also like any student watching to acknowledge that when you have a concave up portion of the solution graph, these approximations are going to be below it. So that's basically what's happening with Euler's method. Now, I'm going to show another slide where we reduce the step size to 1/2. And I think what that's going to help with is understanding the necessity of this column. I kind of alluded to that before, because once again, you may notice that this column matches this column, but that's only because the step size was 1. Now, this column is for the instantaneous slope at any of these given points, that's for sure, but it's really this column that helps us scale the situation to the graph itself, all right? And I do want to also acknowledge, or have any student acknowledge, that in a way, you can notice a pattern within the table. So upon filling out the table, there were a couple things that we could have filled out right away. There was this entire column based on the step size, based on the initial starting condition and the step size of increasing by 1 each time with regards to the x coordinates, right? However, we could have also filled out, the empty parentheses equals, blah, blah, blah. You could just fill out this portion with the step size. So those are things that you could do right away. But as we sort of went through the process and started filling all of this stuff out, you might notice that each new y value is the result of adding this result to the previous y value. So for example, we could have known that this y value would have been 0 because this 0 plus that 0 is 0. We could have known that this y value is 1/2 because this 1/2 plus this 0 is 1/2. We could have known that this y value is 3/2 because this 1 plus this 1/2 is 3/2. And finally, we could have already known that this y value is going to be 3 because this 3/2 plus this old 3/2 is going to give me a 3, and I should put this in green. Okay, so hopefully that makes sense. Let's move on. Okay, so now we have a smaller step size. Everything else is the same. It's the same curve, same derivative, same initial um, point, right? So these yellow boxes are the pieces of information that would be given. Typically, we might not have this. We might not have this in our problem, but it turns out the yellow boxes are enough information to at least approximate the solution curve. Let's go ahead and fill out what we can already. Now the step size here is 1/2, and as I told you before, the smaller the step size, the more accurate the approximation is going to be. So we have that initial point 0, 0. In this case, since it's a step size of 1/2, it's going to go up by increments of 1/2. We'll just say 3/2, and then we will say 2 right there. So that's what's happening with those. We could also fill out these parentheses with a 1/2. And we shall take it from here. So dy over dx, well, it's going to be 1/2 times 0, so that will be 0. 0 there, 0 there, and it's going to be 0 here. So this time we're dealing with increments of 1/2. So now we're only going to go from the initial starting point to 1/2, which is right there. Every time I plot points, I'm going to use the green. So that tells us that the next point is going to be literally 1/2 comma 0, right? You can see that with the green point. Now, with regards to dy over dx, it's going to be 1/2 times that 1/2, so that's going to be 1/4, right? It's going to be 1/4. Now, 1/2 times 1/4 is going to be 1/8. Now, this is the sort of slope that we're going to be taking into account when we graph the scenario. Now, here's where I just want it to be kind of made clear where we could say that it really is the case that it's the instantaneous slope of 1/4 is really what's happening here. But when we scale it to these smaller step sizes, this is really the better way to kind of look at it, because what this is suggesting is that for every 1/2 unit over, we're going to be going 1/8 up. All right. And that is the same as if we were to conceptualize that for every 1 unit over, we're going 1/4 up. Okay, which is what this would suggest. All right, and let's flesh that out. Let's imagine we do that. Okay, keep in mind 1/4 could be thought of as 1/4 over 1, right? So the rise could be 1/4, the run could be 1, right? Think about it. I know that's kind of weird, but the rise could be 1/4, and the run could be 1. So in other words, we go over 1 and then up 1/4, right? Imagine we did that. Well, wouldn't that be, if we take into account a step size of 1/2, that would bring us only 1/8 up, right? And that's why this column is really, really helpful, all right? This column is really helpful because yes, this is the instantaneous slope that's taking place here, that's emanating out of that point. However, we want to scale it to our particular step size, which is exactly what we're doing by multiplying dy over dx by the step size itself. So in case that's not clear, that's what's going on there. So let me get rid of this though. I just want to make sure I erase only that. Okay, so that is the reality with that. So we're going to go 1/2 over and 1/8 up, which is, right around there, right? Because 1/4 up would be here. So actually 1/8 up would be right there. So we'll put a dot there. Boom. Okay. And well, what are the coordinates of that point? Well, that's going to be 1 comma 1/8. Now notice how that same sort of algorithm that I pointed at in the last slide applies here, right? We have that relationship where you could take the result of this column and just add it to that y value, that y coordinate, and then you're going to get the new y coordinate, right? And by the way, that's what you would do without a graph, right? The only purpose of me using the graph right now is to illustrate what this process looks like. Okay, so now we have this column, dy over dx. We're looking at 1/2 x. Well, that's clearly going to be 1/2. So we're going to have 1/2 right there. And of course, that gives us 1/4. So that's going to land us, let's see, when I draw that one, it's going to land us around here, right around there. So put a point there. Now, you might be wondering, well, what is that right there? Well, that is 3/8. Okay, that 3/8 is approximately 0.375. All right. So speaking of 3/8, it's going to be this 1/4 times that 1/8, which is 3/8 right there. Okay. Now, as you can see, when we compare this to the last slide, because the increments are smaller, we're sort of hugging this solution curve a little bit more tightly, right? So once again, smaller the step size, the more accurate the approximation. Okay, dy over dx in this case is going to be 1/2 of that, aka 3/4. So it's going to be 1/2 times 3/4 here. So we would have 3/8. Great. So that is going to be sort of the scaled slope, and that's going to land us at right around here, which by the way is 3/4. Okay, so that's right here. Great. So that's going to be 3/4. Now, one way of knowing that that's the case is it's going to be 3/8 plus this 3/8, which is 6/8, aka 3/4. Okay, so we have one more. This is going to be smaller approximation graph, and that's fine. So we have 2 comma 3/4 is this point right here. And dy over dx is 1/2 of x, so in this case it's going to be 1, which means I multiply 1/2 times 1 over here, which is going to be 1/2. So that is a scaled slope of 1/2 as it pertains to this particular graph. So that's the same as saying for every half unit over we go, we're actually going 1/2 unit up, right? Now, you may also recognize that to be a slope of 1, right? So it's right around there. Now that is 1.25 or 1 1/4. All right, and that's something that we could verify by adding this 1/2 to the previous, to the 3/4, and 3/4 plus 1/2 is most definitely 5/4, also known as 1.25. Okay, now of course we could keep going if we had a larger table, but as you can see, this one is a little bit more tight around the solution curve. So that's essentially what you're doing with Euler's method. With Euler's method, you are choosing a step size, right? And you are analyzing the instantaneous slope at each new point that you're generating. And that instantaneous slope will always be such that it keeps you relatively tied to the original solution curve. Okay. So anyway, hopefully that's helpful for all the students who are taking their AP Calc classes. If you have any questions or comments, if you saw that I made a mistake anywhere, please comment below, and I will talk to you later. Bye.